4.2 talks about linear approximation and differentials. Well, linear approximation, suppose you have the following curve. Let's say that's y equal f of x. So if I pick a point on it, let's say A, that would be A f of A, x and y basically. And if I was to draw a tangent line, the tangent line would look like that. Now this is the idea. If I want to figure out a point on the curve, it's very hard to use because as you see, that's not a smooth curve. I'm not sure, that's not a straight line. So whatever this curve is, as long as I stay around A, I would use the line instead of using the actual curve. I will be off by that much. Or if I'm below, I'll be off by that much. The catch, I need whatever I'm evaluating to be very close to the point that I picked. Now, the function is y equal f of x. And y equal f of x could be a sine, it could be a cosine, it could be a radical, it could be a polynomial, you know. And say I want to figure out the sine of 28 degrees. Well, this is an irrational number. This is very hard to do without a calculator. But if I take A to be 30 degrees, and I know the sine of 30 degrees is, what is that, the official 1/2? So that point will be 30 degrees, except it has to be radians. You can't use degrees every time you want to use linear approximation. So the sine of 29 degrees, if I look at the curve, well, that's hard to pick off of the curve. But if I use a straight line to approximate the sine of 28 degrees around it, within 2 degrees. And if I could use the straight line to approximate what that is, even though my answer is going to be off, right? So there's a sine wave. This is 90 degrees. 30 degrees is right there. So figuring out the sine of 28 degrees will be an issue. But if I find a straight line approximation and use the straight line, that's very easy to do. And how does that work? To find an equation of a line, I need a point and a slope. There's the point. And since this line is a tangent line, I want the slope of it. I know what that is. The slope of the tangent is simply f prime of x evaluated at x equal a that I choose. That's f prime of a. And the equation would be y minus y1 equal m into x minus x1. And if I move this to the right, my equation would become f of a times, right, not equal, y minus y1 equal m into x minus x1 plus f prime of x minus a. Pretty much, this is nothing more than, if I rewrite this, y equal mx plus b, if I was to really clean this up, f prime of a times that. And guess what? That's what the whole fuzz is about. This is pretty much majority of this section. They say L of x, if L of x is the linear approximation of a function, then you could find it by taking the derivative, the slope times x minus a plus f of a. That's simply y minus y1 equal m into x minus x1, and just move that over to the other side. I wanted to show you this to know that every time you see linearization in any course, because when you get to third semester calculus, instead of a line, you find a plane to approximate a surface. Same idea. So let's do that. Here we have x plus x to the fourth. Remember the catch. If you want to use this, you have to stay around the a. So here we have to stay around 0. You know, if I want to approximate that 0.2, 0.1, 0.3, you know, that's not a problem. Around 45 degrees, 46 degrees, 48 degrees. If you want to approximate, use this linear approximation around 60 degrees, you have to redo this. So make sure that you find the equation of the line near a. In this case, if I put 0 in, I get 0 plus 0. That's my point. And my slope is the derivative. The derivative is 1 plus 4x cubed, evaluated at that x value. The slope of 0 is simply 1. I got a slope and I got a point. I could say L of x equal, or I could just say y minus y1 equal m into x minus x1, or simply y equal mx plus b, since that's the y-intercept. So, and this is the linear approximation. It's simply x. So around 0, instead of using this, you could just use x. If they say, hey, tell me what is f of 0.2. Well, instead of saying that is 0.2 plus 0.2 to the fourth, figure this out. L of 0.2 is simply 0.2. And if I work this out on my calculator, just to see how that works, if I take the actual answer, if I take 0.2 plus 0.2 raised to the fourth, I'm going to be off slightly. It's going to be 0.2016. So f of 0.2 is 0.2016. So you're off by 0.016. That's a good approximation. And I could use that as long as all the values I am trying to figure out are around 0. If I want to do this around 1, I can. Then I have to go in and redo this. Plug 1 in, that will give me a 2. Find the slope of the tangent at 2 and come up with the equation again. And that will work around 1, 1.1, 1.2, and so on and so forth. Here, if x equal pi over 4 or 45 degrees, tangent is 1. And the slope of the tangent is simply the derivative. Derivative of tangent is secant squared of x evaluated at pi over 4. And that will be 1 over, let me see, what is that? That's secant. That's radical 2. Radical, so here, really quick. If you're talking about 45 degrees, that's 1, that's radical 2. So secant is the hypotenuse over the adjacent. That's radical 2 squared, which is simply 2. So y minus y1 equal m into x minus x1. If you move that over, the linear approximation of tangent is 1 plus, you could work this out if you want, you could leave it as it is, 2x minus pi over 2, and L of x is simply 2x plus 1 minus pi over 2. Remember, pi over 2 is about 1.57. So as long as I stay around that angle, I could figure out the tangent, which is an irrational number, around any of these values. And again, remember, without a calculator, figuring out the tangent of 20 degrees is a lot of work. We're going to do the same here. We're going to say, well, let's see. For the following exercises, compute the value of the given within 0.01 by deciding appropriate. Let's not worry about that. Let's worry about what we just talked about and use common sense. We want to find a linear approximation. We're going to check on a calculator. We want to figure out what that number is, but we're going to use a linear approximation. So I'm going to say, let f of x equal x to the 6. And I'm going to say let a equal 2. Well, if a equal 2, then 2 to the 6, that's 2, 4, 8, 16, 32, that's 64. And if I take a derivative, that's 6x to the 5th, evaluated at 2, that would be 6 times 32. That's 160, I think. 150, no. 180, 192. Yeah, 32 times 5 would be that. 180, 192. So I could say y minus y1 equals m into x minus x1. I could say the linear approximation is simply 64 plus 192x minus 418. Of course, use a calculator for all of this. And that would be 192x minus 320. So I claim around 2, you could use this instead of that. Now, if I want to take 2.001 to the 6, I'll have to multiply that by itself 6 times. Or I could say, look, what is L of 2.001? That is 192 times 2.001 minus 320. Now, it's true you're going to multiply that, but you're going to do that only once instead of doing that 6 times. You get the answer, you multiply it by 2.001. And imagine if that was to the 60th power, then the same deal will happen. And what would this be? Well, let's see. If I take, and again, I could multiply that by hand. It's not going to take that long, but for the sake of time on the video, I'm getting the answer to be 64.192. 64.192. That's my approximation. I know that's off. I know that's not the answer. What is the actual answer? What is 2.001 raised to the 6th power? That is 64.1922. That is 64.1922. So I am accurate to 3 decimal places. And if you're going into programming, this is going to be a big deal. Well, how about this problem? I want to figure out the cosine of 0.03. Well, guess what? This one I can't multiply by hand. This one I could multiply by hand 6 times. This one, I don't even know how to do that. But if I go on my calculator and I say, well, let's see, make sure I am in radian mode, and I am, it's R. If I take the cosine of 0.03, I'll get 0.99955, 0.99955, 00337. All right, well, now what? I'm going to say let f of x equal the cosine of x. That's the function. And I'm going to choose a number around 0.03 is 0. If I put 0 in, cosine of 0 is 1. My linear approximation, I need the slope of the tangent, which is the derivative, that's negative the sine of x. Evaluated at 0, that is 0. So simply, my y minus y1, if I have a slope of 0, the line is horizontal, right? And I could simply say it's y equal 1, or I could say y minus y1 equal m into x minus x1, that's 0. I could say the linear approximation in this case is simply 1. Around 0, only around this value. Well, what is L of 0.03? It's 1. So you could see we are off by what? What's 1 minus that? So the answer should be 0.999. What's that minus 1? So I am off to 3 decimal places. I'm accurate to 0.00 if you round this, right? If you round this to right there. If you stop there. If you're going to stop, I'm sorry, I marked the wrong part. If you stop right there, wouldn't that round this up, and that would be 1, 1, 0, 0, 0, and that would become a 1? So this is accurate to 3 decimal places. And it's much easier to use 1 around 0 for cosine than you trying to figure out what's the cosine of 0.001. Again, that's a value that is irrational. It's very hard to find. And that's the idea of linearization. And here's another one. Just make sure we can figure that out. Well, what is that? What is 1.1, right? That's 1 plus 0.1, or if you're not sure what that is, just use a calculator. No need to worry about that. There we go. That's 1.1 raised to the 10th power. Again, you could do that. This one is not irrational. That's 2.5937. That's 2.5937. 4246. Now, let's say you didn't have a calculator. Your option is to take 1.1 to the 10 and multiply it by itself 10 times. Or you could say, well, let's see, f of x is x to the 10th, because I'm raising to the 10th power. And if I go 1.1, then I'm going to choose x equal 1. If x equal 1, y equal 1. And the derivative is 10x to the 9th. evaluated x equal 1 is 10. Y minus y1 equal m into x minus x1. L of x will be 10x minus 10 minus 1 is minus 11. And now if I use L of 1.1, guess what? That's 10 times 1.1 minus 11. That is, okay, something's not right. Let me see what I messed up on really quick. Okay, I found it. I was getting a 0. 10x minus 11. When you add 1 to both sides, that becomes not an 11. So here, there's an extra step in there. Let me add that in there really quick. Shouldn't have skipped and I shouldn't rush. So y minus 1 equal 10x minus 10. When you add 1 to both sides, that becomes a 9. There we go. And this will be 11 minus 9, which is 2. So this is accurate to 1 decimal place. Now keep in mind, the faster, the stronger the function increase or decrease. X to the 10 is increasing rapidly. So the further you move away from 0, the bigger this error will be. And if they ever ask what's the error, you subtract the 2, and that's how much you are off. If it's positive, you overestimate it. If it's negative, you underestimate it. Another idea we need to get out of the way, and this is differentials. Again, if I'm looking at a function, let's say I'm looking at one of those. I'm trying to figure out what I want. I want to know what's this value. I'm after figuring out what that y value is. What I do, I draw, again, a tangent line. Let's say the tangent line looks like that. Now, we agree, hopefully, that this tangent line is slightly off. Okay, I did it again. I want to look straight. There we go. So, let's say I moved this much. Let's say I took this x right here, and I added a delta x or an h. Right? Wouldn't that be x plus delta x? Now, there are two values here. Well, check this out. If I move delta x, the change in y is right there. But, and I know we didn't talk about this before, but now we are. Do you see this right here? That's dy. This is the approximation of this. We are off by that much, depending on how far do you move away from x. The further you move from x, the bigger the error is. But we're going to take this as an answer instead of this. This is differentials. This is the actual, the exact. Now, if I have y equal f of x, and I take a derivative of that, dy dx is f prime of x, and if I cross multiply this differentials, this is what it's saying. If you want to figure out the differentials, figure out what this is, pretty much figure out the slope of the tangent times the change in x, and that should give you what that is. Again, if I want to figure out how much your pay changed, well, tell me what your rate of pay is times how many hours did you work? The change in the hours. The change in the hours times the change in rate in your pay will give me the difference, and good approximation of the difference in your paycheck. Now, in general, f of x plus delta x, which is this y right here. So x plus delta x, f of x plus delta x. This y right here is normally f of x, the original f of x, plus delta y. That gives you exactly what that y value is. Instead of doing that, which is very hard, we're going to say take f of x still, we know what that value is, and add to it this d of y, where d of y is simply that. And I'll point that out in an example. So when they say what's the exact change, this is the exact change. When they say what's the approximate change, this is the approximate change. So here we have a function. We just want to find the differentials. Differentials is simply dy. Well, that's simple. Dy would be, well, let's see, dy dx would be what? That would be 12x cubed plus 2x minus 2. And if you cross multiply, you're done. Now, this was very used, again, very useful if you're going to program, because we approximate in programming most of the time. You're going to program a computer to evaluate values or a calculator to figure out values. So for this, it's fairly simple, nothing to it. Find the differentials here. If this is the function, if you start at 2 and you move a delta, so we're trying to kind of figure out, hey, what happens at 2.1? Well, 2.1 squared, you're going to have to multiply that by itself minus 2.1 and combine. If you just take a derivative, not Newton's notation, Leibniz notation, dy dx is simply 6x minus 1, and dy is 6x minus 1 dx. So if you want to figure out the approximate differential in this, put a 2 right there. Okay, that didn't register. Put a 2 right there, and that will be 6 times 2 minus 1 times 0.1. So dy would be 12 minus 1 is 11. 11 times 0.1 is 1.1. So the approximate change is roughly 1.1 when I go from this y value to this y value. I could show you that really quick. If I take y2, if I take 3 times 2.1 squared minus 2.1 plus 6 and subtract that from 3 times 2 squared minus 2 plus 6. Hopefully I didn't mess up on any of those. It's 1.13 and I'm approximating that to be 1.1, so I'm off by 0.03, and that's a very good approximation. Now, why is that? Because this I could do by hand, really simple. Figuring this out is going to take time. Same deal here. Look at this problem. We have a problem with tangent, because tangent is an irrational number. Around 0, if I want to go by pi over 10, remember pi is 3.14. 3.14 divided by 10 is an actual value. So I'm moving by roughly 0.3. Well, if I take this and say, well, dy dx is the secant squared of x, dy is the secant squared of x dx, and the change of y would be simply, again, put 0 in. Secant of 0 is secant of 0 is 1 times pi over 10, which is roughly pi over 10. And we just got that answer. That was 0.31. Oh yeah, 3.14 divided by 10, 0.314. Okay. Versus, if I really wanted to figure out the tangent of pi over 10, that's a problem. That's an irrational number. I'm not sure what that is. If I do the actual value, if I take the tangent of my answer, pi divided by 10, I'll get 0.3245. 0.49, so I'm accurate to 1 decimal place. And that's a very good idea of how much change there is, and that's really how this plays. And the same deal here. If I want to figure out what this is, well, the differentials dy dx will be product quotient rule. Denominator times derivative of the top is twice the cosine of 2x minus derivative of the denominator times the top divided by the denominator squared. Dy will simply be x twice x cosine of 2x minus sine of 2x divided by x squared, oops, times the x, correct. And if I really want to figure out what this is, evaluated at pi dx, I'll get dy to be, oh, I forgot the pi right there. That will be 2 pi, cosine of 2 pi is 1, minus sine of 2 pi is 0, divided by pi squared times 0.25. I'll say the approximate change in the y value would be 2 pi divided by pi squared times 1/4, and the approximate change will be 1 divided by 2 pi, 1 divided by 6.28. I could do that division once and I'm set. Instead of me trying to figure out what's the sine of 2 parentheses pi plus 0.25, which is again is an irrational number, and by now we lost track of how to do that. Okay, how about this problem? And again, this is a use of it. For the following exercise, find the change in the volume or the change in the surface area. The volume, I have a cube. If I have this cube, what's so special about a cube? All of these sides are equal. If I wanted to paint it, if I was to put a paint, so find the change in volume if the sides of the cube change from 10. Initially there were 10 each. So if I put a paint on that, or I put what do you call it? A texture on it, in which I increase that by 0.1 on each side. How much texture should I purchase? How much do I need? Well, do you know what the volume of a cube is? The volume of a cube is x cubed, right? And the exact change is dV. I'll find that out in a minute. That's basically the new volume, which is 10.1 cubed minus the old volume, which is 10 cubed. But if I want to use differentials, I'll say dV dx is simply 3x squared, and the change in volume is roughly 3x squared dx. So the change in volume is going to roughly be 3 times the original times, what's the change from 10 to 10.1? So dx is 0.1. This is 100. That's 300 times 0.1. The change is roughly 30, whatever the units are cubed. If I want to figure out the exact change, I'll take this 10.1 cubed and subtract off 1,000. The exact change is 30.301. Let's say that is centimeters cubed. Well, this is the exact, and look, without a calculator I was able to get what that is. How about the change of area of a sphere? Well, we have one of those things. Sphere depends on the radius. The surface area is simply pi r squared. Right? Yeah, it is pi r squared. So an approximate change dA dr is 2 pi r, and dA will be 2 pi r dr. There it is. Tell me what the radius is. Tell me what did you change in the radius, and I could tell you if you want to paint that or coat it or coat it or put something around it, how much material you need to buy. And here's another one. circular cylinder, one of those, r is 2, and the height switches from 3. Initially it was 3. You're going to go to 3.05. So the change in height is 0.03. Well, the volume of a cylinder is pi r squared h, but the radius is fixed. So the volume is 4 pi h. dv with respect to h is 4 pi, and dv is roughly 4 pi dh. So the change in volume is roughly 4 pi times 0.03. And isn't that 4 times 0.03? Wouldn't that be 0.1212 pi? Okay, and here's one that's going to come up a lot. I want to find the linear approximation of this around x equals 0. So if x equals 0, put 0 in there. You get 1 to the k. 1 to the k is 0. The derivative will be k into 1 plus x to the k minus 1. Evaluated at x equals 0. If you put a 0 there, the derivative is simply k times 1, which is k. So wouldn't the linear approximation of this be y minus y1 equal m into x minus x1? Wouldn't y equal kx? So 1 plus x to the k is roughly something. Oh, when I put 0, I get 1, not 0. People, when I put 0 in there, I'll get 1 to the k, which is 1. So y minus y1. So that's, move it over, 1 plus. So this is roughly 1 plus kx. But that only works with one condition. If you take in 1 plus x raised to a power, k, it ends up being 1 plus the product of those, as long as x is very close to 0. And here's a use of it. If we want to figure out what this is roughly around 0, I could take this and say, look, that is 1 minus x squared to the negative 1/2. That's roughly what's taking the place of x. It's not matching. It has to be 1 plus. So I'm going to say that's 1 plus a negative x squared raised to the negative 1/2. What's taking the place of x? What's taking the place of k? So this is roughly 1 plus a negative x squared multiplied by k. So the linear approximation of this is roughly 1 plus x squared divided by 2. And that's pretty much it for this section.